Okay, so we're very glad to have our next speaker with Burgess, who's going to talk about post-Planck naturally.
Thank you. Is the mic on? Good, thanks. So thanks again. I want to, well, actually, Liam said this, but I'd like to reiterate thanks for the invitation to speak. Cambridge runs a great meeting, and as you all know, it's been great to be here. So I kind of gave this vanilla title because I want to talk to you about non-Gaussianity, and then Planck cut the legs out from under me. And so this title was broad enough that I could talk about anything, essentially. And so, but the theme will be naturalness. I think naturalness is something which is, we wonder about it because it's something which has been guiding us for a long time in particle physics and in cosmology. And it seems to have told us we should be seeing things which we're not seeing, as I'll say in a second. And so I want to make the case largely in this talk that keep the faith, because it's I think that what we're seeing is not so crazy given what you would expect from naturalness. But you should take the point of view that I'm mostly going to be talking about string inflation, and I'm kind of, this morning we're having a string inflation, a string sandwich, and I'm kind of the natural filler between Liam and Joe, who are the hardcore string people. And so I'm going to be talking about, I say that because when I talk about string inflation, I actually have no axe to grind about string theory. It's a beautiful theory, but for me, it's really, what's nice about it is that it's a picture for an ultraviolet completion for gravity, which is concrete enough that you can ask all these questions that you like to ask. And so if someone else comes up with their favorite picture, then once it says concrete as string theory, then we should all look at it too. But it's really a wonderful framework in which to ask cosmology questions. All right, so the naturalist story in cartoon form has been that the high priests come down from wherever particle physics high priests come down from, and they tell you that naturalness is this clue that nature comes to us with hierarchies of scale. We don't have to understand them all at once. That's why science progresses. Most of the stuff about small distance physics is irrelevant for long distance physics, and that's wonderful. That's why we didn't need to know nuclear physics to discover atoms and things. Cosmology, you might have thought then it doesn't depend at all on the smaller distance physics, and so why do you talk to particle physicists at all? But it happens that there are a few things of small distance physics that can be important at large distances, and in the atomic nuclear example, you did need to know the charge and the mass, say, of the nucleus to say things about what's going on in the atom. And it happens that what people talk about in cosmology, typically vacuum energies or very shallow scalar potentials, those happen to be things that are very sensitive to what goes on at small distances. And so the hope is that what that means is that it's difficult to get what you like in cosmology from a microscopic theory that makes sense in other ways. And so that's a clue, and we should not ignore clues like that. It's difficult to believe that we're going to have measurements in cosmology that will in themselves distinguish all the many cosmological models for dark energy or inflation or whatever. And that's probably true, but that's not really the point. One of the important clues is that whatever is working in cosmology should be part of the story of what's going on everywhere else in all the other experiments we do. And if it's hard to get cosmology from other kinds of physics, then that should also be narrowing down our choices of the things we're trying to compare with experiment. But that line of thought has told you that the LHC should see lots of new SUSY particles, and inflation probably has, if you're going to have a shallow potential for inflation, it's going to be hard to get, and so there's probably other things going on, and so it wouldn't be surprised to find inflation's complex. And of course, that didn't really work out so well. So if you go to ask how SUSY's doing at the LHC, there's this really great exclusion plot they had at SUSY 2013 a couple weeks ago, which you can look it up on the net depending on what your internet settings are. It's kind of a bit of a racy plot, and so there's a bit of a buzz out there. If you Google SUSY exclusion plots to SUSY 2013, you'll find that plot. But I had to cover it up because even I couldn't put it on the screen here. So. But the upshot is that they're not finding SUSY, so it's kind of it is exclusion plots that they're seeing at SUSY 2013. And of course, the joke is that the supersymmetric top is the stop, and the only one they've seen at CERN is the one by the gate. And a similar story for Planck, right? Planck is, we've seen these plots, and the message of Planck for a theorist is simplicity. You're seeing simplicity. If you thought that you should be seeing complexity, you were wrong. And of course, if you're talking about the cosmologic constant is the elephant in the room. If you're talking about naturalness, that's the one that nobody talks about. In the SUSY meetings or cosmology meetings, that's the real problem. That's probably the biggest problem with naturalness arguments, is that it should have applied everywhere. And so what about the cosmologic constant? So is it dead? Observers and astronomers are experimentalists are conservative people, and if we go to a conservative intellect like Sarah Palin, she has this quote, "How's that hopey-changey thing working out for you?" It's, and I think that's a legitimate point of view that we've all had, given how things have turned out. So the point of this talk is based on another one of her quotes, that is that it's not dead. I want to make a case that actually what we're seeing is not so crazy to have been seen, and so keep the faith. So this is the way I'd like to do it. I'm going to mostly talk about inflation, given what this meeting is, and I'll talk about inflation walking the Planck, and so there's this, I'm sure that many people have made this kind of analogy. I want to first talk a little bit about the context. There is a discussion in the literature about what Planck is saying about what fundamental physics might mean for cosmology. Then I want to talk about this basic a difference in picture between the way you think about cosmological models, the Occam-Razor approach and the Wilson action approach. And then I'll talk specifically about string inflation, because that's my area of expertise, and I'll give a scorecard. And so the kind of nature of the Planck you're walking has changed a little bit. It's more like reality TV than it was back in the past. And then I'm going to do the thing that they say you should never do. I'm going to actually have a second topic, which is I'm just going to do very briefly, because many of you will know that I'm one of the few people on the planet who thinks that there actually is a solution to the cosmologic constant problem. And I've had two messages in this very, very telegraphic last part, which I'll get to. One of which is that we're still here, and it's still working, and I think it's actually working better and better. And the reason that the rest of the talk is not about that is not because it's dead. But the more important thing is that Matt William will talk more about this in the afternoon, and I want to draw your attention to his talk, because he's found a very interesting thing. One of the nice things about this approach is that there's quantum corrections are smaller than you think, and I think Matt has identified why. And so I'll give a very brief statement about what I think the reason is, and then Matt has much more details in this afternoon's session. All right, so let me go back to the context. So there's a discussion in the literature about what Planck means for inflation and for other models of inflation and other models of what's going on that are not inflation. And I won't tell you who wrote those, but you probably can guess from the titles. And so I must say I don't actually disagree strongly with the attitude or the points of view that are put forward in these papers. But the first one I think is probably a little bit overstated, and so it kind of brings to mind the Mark Twain quote that the report of my death was an exaggeration. And the second one actually I'm more sympathetic with. But since I was looking at Mark Twain quotes, I found another one which actually applies to it. And it says, "I didn't attend the funeral, but I sent a nice letter saying that I approved of it." But the message that they're saying in these papers is actually a good message. It's that we should be questioning our assumptions, given that we've had this new slice of data. And so there's 2 points being made in the inflationary paper, one of which I'm less sympathetic to, but the other one I think is a good one. The first one is just that I think the whole paradigm being in trouble has 2 parts to it. One of them is that if you had a prejudice about inflation, should have meant things like phi squared models or phi cubed models or something simple like that, then they would be in trouble. But of course, this plane is populated by models, single field models, and so that's not really, I think, the main point of this paper. The main point of this paper is that there are conceptual problems with inflation, some of which are listed here. Inflation was invented to be a theory of initial conditions, and yet sometimes in constructions you need special initial conditions to get inflation, and so then you're kind of not really solving the problems you set out to solve. You need particle physicist balk when you've got a scalar that's lighter than the higher scales that you're ignoring, but in inflation you need something lighter than that. You need it lighter, so small that it's lighter than the Hubble scale, which is Planck suppressed. You need to ask for fields to run over trans-Planckian distances to get observable tensor modes, with some exceptions. How do you reheat? If you're amplifying things and seeing quantum fluctuations, could you amplify sub-Planckian physics? The whole problem of how you handle internal inflation, all those things I think really are issues to think about, and we should be trying to think carefully about them. And what they do is they drive you to models which are more complicated. Answering these questions all of these questions involve in some way asking how inflation sits within an ultraviolet completion or inside some sort of a more complicated microscopic picture. This one, most obviously, if you to ask how trans-Planckian intrusions could occur in inflation, you have to know what they are and what it would mean to talk about them. But more generally, inflation, the basic picture you have is that you're seeing quantum fluctuations. So it's the one place where you're saying that quantum fluctuations in gravity are not negligible and they're observable. And so the whole issue of how you control quantum fluctuations in gravity is central to the whole story. And so that means that you're not too far from the point where quantum gravity is important. And so the understanding of the interplay between quantum effects and gravitational effects is really central to the whole story of primordial fluctuations. The cyclic models are, they're looking for an alternative, and I think they should be. And I think it's important that people do that. So I want to agree with that point. But I think we also have to distinguish right now, at this instant in time, between when you're advocating your model or when we sit back as a field and say, what's the preponderance of evidence? And I think right now, the reason that the preponderance of evidence supports inflation is that cyclic models, they also have issues where you need to talk about an ultraviolet completion. And most notably, everybody's agreeing that the primordial fluctuations look like there's been acceleration. And the issue is it acceleration that takes a contracting universe to an expanding one, or is it just one like inflation where everything was always expanding? So you need a bounce in the cyclic models, and the question there is, how do you control the bounce? And so I think when you're describing the preponderance of evidence on these models, what makes these ones less attractive now is that the central mechanism requires an access to ultraviolet completions, whereas in inflation, the basic inflationary mechanism doesn't require you to probe ultraviolet completions. These other issues that are complications of inflation do, but the central mechanism in itself doesn't. And so that may change, and I think that's why you study these models, is you try and find if you can understand bounces. But I think right now, what you'd have to say is that that's a qualitative difference in our understanding of these two classes of models. So how do we do? So let me first talk about the Occam versus Wilson story. Why do you think about complicated models? And I've partly told you about that. And to set that up, this is my favorite picture of a place in Cambridge. It's just around the corner on Grange Road. You can probably recognize the street. And it kind of, when I show this slide, I showed this slide and there was silence in the room. I show this slide in North America and people giggle. And that's because in North America, if you saw something like this, Americans and British famously are divided by a common language. And what this says is that this is a place where large African animals cross after they've had sex. And so it's, when I saw that, the second best slide is there's another one that says humps for 550 yards. So there's a similar thing going on in cosmology and particle physics. There's a different language that is used often in particle theory and cosmology theory. A cosmologist, I think, takes the Occam approach when describing something like the primordial fluctuations and asks, what's the simplest possible model that describes it, and then doesn't complicate the model until the data drives you to complicate it. And that's certainly a reasonable point of view to take. The Wilson point of view is the one that particle physicists often take, and takes the point of view that what we're looking at is the low energy limit of something, and that's often a messy thing. It's often not as simple as you would like it to have been. And so that doesn't say that you're looking for complexity for its own sake, but it does say that what you're looking for are questions that are kind of generic to the degrees of freedom that you think are relevant to the scales you're trying to describe. And so Liam's talk is actually a great example of that it's, you're trying to strip away the details of the microscopic physics and ask what was generic about the low energy theory. And if some features are complicated, then that's life. And the standard model itself is a great example, and searches for beyond the standard model are like that. When we know that the standard model doesn't give us dark matter, it doesn't give us dark energy, but there's the mainstream search in particle physics has not been for the standard model plus a dark matter particle. You're looking instead for things like supersymmetry or things that are really dealing with the kinds of that would make the standard model look like it should have appeared at low energies in a natural way. Now, I'm not saying that you shouldn't make models that have just simple dark matter extensions, because that allows me to make a shameless plug that you might be reading some of my papers if you did. And so I think what you want to do is you want to compare the simple model point of view to the generic model point of view, and it's the comparison of those two things that gives you something that you can learn about. So I've told you already why you embed these things, inflationary models in particular, into ultraviolet theories. You're trying to make progress on these issues like initial conditions in large fields. And so you'll kind of see along the way how we've done. I think there's many of these problems that progress has not been made on, and I think the internal inflation one is the one that people worry about the most. The only comment I'd say there is that the eternal inflation problem, which is the problem that if you have inflation going on anywhere in the universe, it can take over, and then the question is, if you have if you have a landscape of solutions, some of which can be inflating. The question is, how do you make predictions? And that's often posed as a problem for inflationary models, but really it's a problem for any theory that it has a landscape of solutions. So even if you were, say, believe in cyclic models or some other models, the problem of internal inflation happens if elsewhere in the landscape there's inflation going on, then all the problems kick in, even if you didn't want to use inflation as your basic mechanism. It's a generic problem that is not really differentiating inflationary models from other ones. It's a, I think, important conceptual issue, but it's not something which has actually been an obstacle in interpreting, say, the Planck measurements in terms of simple inflationary models. But it needs to be understood. So what's the scorecard? I'm going to take the different point of view from Liam here in that, it's often said that, so this is all very nice, yada, 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 think about string theory, but you can get anything from string theory, so you're not going to really be able to tell me anything useful. So one way to test that is let's just see how string models did. And so what I'll do is I'm going to take, this is a summary talk in 2008 by Joel Polchinski, where he was summarizing all the things that were the string inflationary models of that time. And that's the main categories were already there. And so this is the old WMAP plot of the scalar tensor ratio against the spectral tilt, and these are a bunch of models that the WMAP people had put in. And these extra colored ones are the ones that Joe added to the plot, and he's labeled them by, in this case, it's this is the acronym of the authors of the paper, but then these are speakers at the meeting, and so these are the models they had talked about. And so if I transfer that to the Planck plot, there they are. It's these models here. And there's only one dot here because, in the Planck, these are the other models that Planck had already put, and they had a little line. I just took the lowest of the dots in the line there. So one thing you take home from this is that, the vast majority of models, except for two models, they're all actually on the axis here. You can't even plot their value for R because it's so small that you can't see it here. The exceptions are these two models. And these two models were written down essentially because people had realized that in inflationary model building, it was difficult to get R to be even on this plot. And so a real effort was made to try and make R as large as it could be. And this is the result of that, is that this one is actually just barely on the plot. And this is the monodromy model, which is you can actually see on the plot. But what I get from that is that, so people really worked hard to make R large, and it was difficult to make it large enough to be in danger from the Planck data. And so that's actually something which is unusual. That seems to be something which I think it's not fair to say yet that it's a blanket prediction from string inflationary models, because there's lots of models and they haven't all been explored. But that's something which is emerging as something as what these models do, is that they don't like to give you large tensor to scalar ratios. And the central value here, these are all kind of in a nice place, but that's partly because people knew about the WMAP data when they were doing them, and so you tend to get, no one was giving you blue models at that point because we knew that they weren't supposed to be there. So the way you get the predictions in these models, like Liam said, is they're generically, they're multi-field models, and there's some complicated motion going on. But typically what happens in inflation is that you're only really seeing a specific epoch in the sky now, and so the observational consequences are coming from horizon exit. And in a complicated multi-field potential, it's often true that you're not doing anything interesting at that epoch, and then you can describe it by an effective single-field model, and this is just supposed to show you that. In one of these models, one of these is a numerical evolution to the multi-field potential, and the other one is just a single-field, emergent scalar potential that captures the same physics. So when I describe these models, I'll be doing it in terms of this effective model, effective single-field model. And then you can use these standard formulas that tell you that you have these two slow roll things, and they're related to the observables in this way. And the only thing I want to get you remind you from the slide, because I know you know these formulas, is that the eta is linear in the second derivative, epsilon is quadratic in the first derivative, because that'll play a role later on. So now I'm going to choose to look at, in particular, this smear here along the bottom here are various kinds of models where the inflaton was a modulus in the extra dimensions. And I want to emphasize, though, just because people talk about these models, because they give you a potential like this. They give you an exponential potential, and they do that for a very general reason. They give you an exponential potential because what you're talking about is the field that you're talking about, the motion of, is the size of some handle or something in the extra dimensions, so some like radius. And you only really believe you can do those calculations of how those moduli behave when the radius is large compared to the string scale. So you typically, when you find the energies associated with changing the size of that radius, you get something which is a series in 1 over r because you're in this large radius limit. So there's a bunch of terms like this. But the canonical variable you should be using when you use these slow roll expressions is the one for which the kinetic term is just d phi, And if you dimensionally reduce the Einstein action, you find that these radii typically come in as dr over r squared. So log of r is the thing that's the canonical variable. So you have some relationship like this. And so the domain in which you believe everything is when r is much bigger than the fundamental scale, and that's when phi is large, is basically the point. And if this were canonically normalized, it would be large in Planck units. Now, with this kind of a potential, this is what's nice about this potential, is that it's basically the one that's equivalent to the Starobinsky r squared thing. That's why it's essentially in that part of the plot. But more importantly, because it's an exponential, a nice feature of this model is that it makes the flatness of the potential is a consequence of phi being large. It's a large field model in that sense, although it's not a large field model in that it's giving you a large tensor modes, because the potential is not going anywhere interesting as the field gets large. So if you differentiate this thing once, you get an exponential. You differentiate it twice, you also get an exponential. And then just because the slow roll parameter epsilon is the square of the first derivative, you get the kind of robust prediction that epsilon is going like eta squared. And so that's something which is interesting, because it says that r is kind of the order of ns minus 1 squared. And so it's small, but it's not so small. Depends on the value of k, of course. If k is very small, then it would be small. But there's a class of models here where you're sensitive to this kind of you're making this kind of a prediction. And then what's hard in these models is to get the 1. That in this kind of picture, the energy is falling off as the radius gets large, and you're asymptoting to some space. And if it's an asymptotically flat space, which it often is in these supergravities, because supergravities have a scale invariance in them, then you don't tend to get the 1 here. But it has been possible to engineer things where you have other fields that are kind of hung up in the potential somewhere, and where the asymptote is a non-zero value. So they're interesting models, and it's suggestive that the Planck data points you towards these models. And the main message I'd leave you with here is that the scalar tensor way of phrasing those models is probably more instructive than the r squared way of phrasing them, although they're essentially the same from the point of view of the observational consequences in inflation. The reason that I make that distinction is that this kind of a model is actually easy to get from an ultraviolet completion, where it's harder to get the particular kind of r squared model, except through the duality that takes you from the scalar tensor theory to the r squared model. All right. Now so what was making these models work is that r was small, and the simplest argument as to why it would be small is that you had to have a trans-Planckian roll, and I say had to have in the sense that you didn't really have to have. There's a famous argument by Leith about that relates the value of r to the distance you move in field space, and it's not a theorem in the sense that it depends on how things roll between horizon exit and the end of inflation. So I want to head off one of Anupam's questions, that this is not a requirement, but it's often true. And so in particular, the issue I'm focusing on here is whether or not, when you look at these string inflationary models, it is essentially true that you're looking at trans-Planckian motions. And so one of the virtues of those models is you can ask geometrically what would that have required, and why was it difficult to do. And so in some of the examples that Liam and collaborators have explored, the problem was that in order to have phi roll that far, something would have to move in the extra dimensions farther than the extra dimensions are big, say. And so by translating it into a geometrical argument, a quantity, you can have a physical statement about how likely it is. And so that appears to be what's underlying the difficulty in getting large r. The other thing that, of course, Planck was about was non-Gaussianity. And here's what they saw, and of course it's small. And in these models, there were two kinds of ways in which non-Gaussianity could have been there. One of them was you could have these non-minimal kinds of DBI models where the kinetic terms are interestingly different, but yet still under control. And those famously do give you non-Gaussianity, and so they're constrained. It's also that since you have multiple field models, you've got lots of ways in which you could have got non-Gaussianity. And so what you find is that you can implement the curvaton or the modulation mechanism in them, but they're not generically there. And so the absence of non-Gaussianity isn't in itself telling you a whole bunch about these multiple field models, because they very often when you make them, they generically are in this single field limit. And so although non-Gaussianity could be there, it needn't be there. So the bottom line is that if you kind of stood back and said, what did the models look like before Planck came along, they looked great. They were putting you into the sweet spot of where Planck put us. The NS value was something which was kind of already, people knew where they wanted to go, but the smallness of R was something which was, it's still difficult to get a model which has R large enough to be in difficulty with the Planck data. How am I doing for time? 11, okay, that's good. So let me switch to the second part, and that's the cosmologic constant thing. I have to say, I go to the particle physics meetings. Everyone's down in the dumps because the Higgs is so simple and there's no supersymmetry. And I go to cosmology meetings, and there's no non-Gaussianity, and the world sucks. And I'm the one happy person in all those meetings, because I think you're seeing everything you should be seeing. And I think the cosmologic constant problem is telling you why. But I have to tell you that I was recently in a dark energy meeting, and it's kind of funny being in a meeting like that, because you have a sense that there's no consensus at all. And so you have the sense that you're in a room full of Napoleons, and you're saying, but I'm Napoleon. They're all crazy, but I'm Napoleon. And so I think it's true that it's a high bar to say that you've solved the cosmologic constant problem, and that's why I think people are skeptical. But I want to tell you that so we're beavering away at it, and I still think that there's a solution here. But so my purpose here is to just give you a telegraphic, what the idea is and what the new thought is, and it's not really a talk about that. So the basic problem, remember, is we believe the vacuum is Lorentz invariant because if it wasn't, we would have seen it in atomic physics, so it's a very good approximation it is. We believe that the vacuum energy would, because of that, be proportional to the stress energy, proportional to the metric, so it's a cosmologic constant. Its size, we think, is large. I'm saying it's the mass, a particle of mass m will give you something of order m to the fourth. You might have said it was the Planck scale to the fourth. I disagree with that, but for the purpose of the argument, just think I'm very conservative. It's a very small number. Already the electron is 10 to the 30 times too big. The top quark would be 10 to the 50 times too big. So if it's 10 to the 122, even more so. The problem is that we think the energy is large, but what we measure is curvature. Curvature is the acceleration of the universe. And then Einstein tells us, well, they're the same thing. And that's kind of the problem. And it's such a simple problem, it's hard to believe that there's a solution to it. And so the basic idea behind where I think the solution lies, even if the direction I'm pursuing is not the solution, I think where you'll find the solution is that an important part of that story was 4 dimensions. That we only know the vacuum is Lorentz invariant in 4 dimensions. It certainly doesn't have to be Lorentz invariant in the dimensions that we don't see. We only measure curvature in the dimensions that we see. If we had a vacuum energy in the 4 dimensions that's Lorentz invariant, nothing says it has to curve the curvature that you measure in cosmology if you have more than 4 dimensions. And the existence proof that this can happen is a cosmic string. If you have a cosmic string, if this is a cosmic string and you think of its world sheet, it's Lorentz invariant on the world sheet, and its tension would be a Lorentz invariant energy density, and yet you know how to calculate the gravitational field of a cosmic string, and it's flat. It's flat actually everywhere, locally flat. It's a conical singularity where you take a slab of space-time and you take a wedge out and you identify the opposite sides where the apex of the wedge is where the string was. Then light rays would focus around the string because the ones that hit the wedge kind of come in the same angle. But the main thing is that for any value of the tension of the string, the induced geometry on the string is flat. And so what you try and do is do this with 2 more dimensions, and we're living in something like that. That's the kind of thing you'd like to capture. It would be a Lorentz invariant vacuum energy in 4 dimensions, which was curving something but not what you see. That's the way in which you try and find a solution. But that in itself doesn't solve the problem. You have to ask, there'll be solutions that look flat on your cosmic string. There'll be solutions that are not flat, and you want to know what choices do you have to make them flat, and are those choices stable under integrating short distance modes out? That's the cosmologic constant. You have to re-ask it in higher dimensions. And the short version of that story is that with extra dimensions alone, generically, you don't make any progress, that you find that the choices you make when they get perturbed by loops by an amount which is similar to what you would have said in the cosmologic constant problem. But the exception is if the extra dimensions are supersymmetric in some circumstances, because for one thing, supersymmetry in the extra dimensions can forbid a cosmologic constant in the extra dimensions. That's one way of seeing it. But what you find is that there are some supersymmetric theories for which the quantum corrections can be of the order of the Kaluza-Klein scale and not of the scales of particle physics, say, on the brains. And so the thing I want to focus on is why was that true? What's the mechanism? And so this is the takeaway point. And this is what Matt will talk more about this afternoon. There's 2 features in these models that are making it happen. And those are the 2 features I'm going to focus on. So the accidental supersymmetry feature is that if you have a brane coupled to the fields in supergravity, and you look at its Lagrangian in a derivative expansion, it starts off with a tension, this is normal, and then the first thing that happens with one derivative is that you can couple, there's a magnetic charge that it can have for the fields that live in the extra dimensions, and then there's higher terms. And the important thing is that if you take the supersymmetry, if you ask, does your compactification break supersymmetry or not, you first ask that in the bulk. You ask, there's a differential condition for whether or not supersymmetry is preserved. The 6-dimensional supersymmetries, are they surviving to 4 dimensions? And so you can ask that question, and it turns out they do in some of these solutions. And then you can ask, do the boundary conditions that the brane set up ruin your ability to find solutions that are supersymmetric? And the surprising answer is that they don't. They needn't. well, it's not so surprising at one level. There's a BPS condition. If there's a relationship between the tension and this magnetic charge, then it can be true that supersymmetry is not broken. So if you didn't have the charge, then it would be broken. That's the picture that people often have. The surprise here is that this condition here is not a condition, it's not a restriction of these numbers in the Lagrangian. It actually depends on the value of a field in the extra dimensions. And it's a field which is a flat direction field, and that means that it's not determined by any of the equations of motion in the extra dimensions because of a classical symmetry there. It's determined by flux quantization. And so this relationship is something which, once you solve the equation of motion for this field, which you will do by using flux quantization, you will learn whether or not this is satisfied or not, even if you hadn't made special choices for T and A. And the amazing thing is that for some of these solutions, when you use flux quantization, it happens that the field adjusts to the point where they are supersymmetric. So the branes can be supersymmetric for any value of their tension, and that's one of the amazing features. Now, the second part of the reason supersymmetry breaks and you get a non-zero answer is that this is an example of something which people have looked for a long time. If I arrange for supersymmetry not to break at one brane, in these extra-dimensional models, there's often more than one brane. And so the field has to adjust in such a way that supersymmetry is not broken at any of the branes to have supersymmetry not be broken at all. And the generic situation is that even if you make things supersymmetric at one brane, it's not at all the branes at once. And so because of that, at any one point in the extra dimensions, things are supersymmetric. But if you take the whole extra dimensions together, you see that supersymmetry is broken. And so then if you want to have a quantum effect produce a vacuum energy, which would require you to see that supersymmetry broke, it has to have a wavelength long enough that it sees the whole extra dimensions. And that's why the Kaluza-Klein scale is coming out as the size of the vacuum energies in these models and not a more fundamental particle physics scale. So that's kind of what's going on to make the quantum correction small. So even if you don't care about the cosmologic constant problem, it's a very interesting and novel way in which to break supersymmetry that is likely to have many nice naturalness features. The picture is great because it makes lots of predictions. If it's wrong, we'll know because you'll have to see a lot of things. I tick off for you for convenience the ones that are right already. You should not be seeing the MSSM. These were made before the LHC and the Planck went up. You should not be seeing the MSSM, and the Higgs is probably vanilla. And so I'm happy that nature got that right. And we're going to move on to the rest of them. So it sounds crazy. You need extra dimensions. You need them to be large. You need supersymmetry. There's no evidence for either of them. But as Sherlock Holmes says, that when you've eliminated the impossible, whatever remains, however improbable, must be the truth. And so the problem is not that we have lots of solutions to the cosmologic constant problem. If you have one, that's probably the way nature works. So here's my summary. So for the inflation story, things are looking gloomy if you thought that it was going to be complicated. It's not gloomy at all for Slava. He didn't think it was going to be complicated, and he was right. And so. But it's not really an argument against naturalness. I think the evidence for simplicity is not evidence that there was not complexity there. It's just that generically these models are not, the signatures like non-Gaussianity could have been there, but they needn't have been there. The questions that you'd like to answer, the questions about inflation that you want to answer, in addition to agreeing with the Planck data, most of them require reference to an ultraviolet completion of some sort. And those include initial condition stories. If you're looking at earlier times in the universe, you're probably looking at higher energies when the universe was still smaller. If you're trying to understand eternal inflation or transplanking issues, these things, or bounces, they all require reference to a more complete control of quantum gravity. And so, although simplicity is nice, anyone who's in the business of understanding those issues does not have access to simple models. The simple models have to be argued for, and it's not a prior you get to put in. And so it can come out of these models, but it's something which is it's not something you're allowed. You can't take the point of view that I want to convince you that inflationary models solve the initial condition problem, but I'm going to only look at very simple models where I don't really get to probe the initial condition problems. And so it's so I think string models look good. They predicted where they said you should be, we were. But I think there are very many conceptual issues that need sorting out. The dark energy story is I'm a lonely voice in the wilderness, but I'm telling you that dark energy, I think, is telling us to double down. If you had your bet on supersymmetry or on extra dimensions, then you want to go again. Even though things are looking bad now, now's the time to bet big or bet small and have large odds in your bet, because this is, I think, this is, I think, what nature is telling us, that the only picture that gives us a small vacuum energy, and vacuum energy is one of those things that the large distance physics is sensitive to, requires both of those things. And so it points to a very different way of realizing. It says that supersymmetry should be relevant at low energies, but in a very different way than people have been thinking. The essential difference is that if you take the electron and you do a supersymmetry transformation on it, you don't get a new particle like this electron. You get the electron back plus a gravitino. It had to be a boson, but no one said it had to be a single particle state. And so that realization of supersymmetry is likely what we're being told to look for by the smallness of the vacuum energy. And that means that we should be looking for a very supersymmetric gravitational sector coupled to a very non-supersymmetric particle physics sector. And the great irony would be that supersymmetry is going to come to us from the relativists and not from the particle physicists for the first time when it's measured, in all likelihood. So thank you for your time. I put this up just to guide your questions. These are questions that I thought about the answer to, so these are the good things, and these are the. Normally, if someone says they've got a solution to the cosmological constant problem, he's crazy, and these are the reasons why. So if those are one of the ones on your list, feel free to ask. So anyway, thank you for your time.
Scott?
Why is the Higgs mass light?
Well, in these models, the fundamental scale of gravity is 10 TeV, so it's actually not that light. The reason it's a vanilla Higgs is that there's not a lot of room to put fancy physics between the gravity scale and the Weig scale, and so the fact that the standard model worked so well meant that it wasn't really a ironclad theorem, but it would be hard to make a model where you could hide all the physics between what we'd measured and the scale of quantum gravity to modify the Higgs. But I guess another way of saying it is that the same numbers that solve the hierarchy problem solve the cosmological constant problem. That this is solving the hierarchy problem in the large extra-dimensional way. It says that the fundamental scale of physics at 10 TeV, and the reason that the Planck scale looks large in 4 dimensions is that the extra dimensions are quite large. And it happens that the size of the extra dimensions you need for that are the same numbers you would need if the vacuum energy were the Casimir energy. They both point you towards about a micron in size.
So you can stabilize the.
There are mechanisms here because you're doing back reaction, you can stabilize the extra dimensions, and so there's a sense in which I can't quite do everything I'd like to do, but the actual stabilization of the extra dimensions it's a model building exercise, but there are mechanisms like the Goldberger-Wise mechanism and generalizations out to the 6 dimensions that you can use. Yeah.
I have a question about your proposal about the possibility that we'll actually have 2 extra dimensions and it's like we live on a string. So in that proposal, what you want is for the string tension, which is our cosmological constant, to only affect the geometry in the bulk, but not on the string.
Yeah.
On the other hand, observationally, we know if I have just regular mass, like the sun, it behaves as if it's in 4 dimensions. So it seems to be there's some tension between these 2 things.
Right.
How do you resolve that tension?
Right. So the question is the basic mechanism I didn't say is that if you ask why is it true that if you're on a string there's no curvature on the string, it's because the tension of the string sets up a curvature in the extra dimensions, and that's that conical singularity. And then those things essentially cancel in the effective theory in the lower dimensions on the brane, and so it gives you no cosmological constant. So the question is, if you have a cancellation in that way for the vacuum energy, why don't you have a similar cancellation going on for static masses like the Earth? And so why don't you start ruining things like the inverse square law? And so that's the interesting. Another nice piece of numerology is that the easiest way to think about it is at the linearized level. If you think of a graviton exchange in 6 dimensions, it's the same thing as graviton exchange in 4 dimensions plus scalar exchange, which is essentially the breathing modes of the extra dimensions. So if you take, and it happens that in 6 dimensions, the graviton exchange has a tensor form. If you had 2 stress energies interacting, you have the interaction is T1 mu nu, T2 mu nu minus a quarter of the traces. And that quarter is good because if you had a 4-dimensional stress energy that was proportional to metric, that would be the cancellation that makes the vacuum energy not be 0. But if we're point mass, that cancellation would have changed the mass to something else. So what's going on is that these scalars have a mass. So if you're looking at distances that are small compared to the mass of the scalars, then you have this cancellation going on. If you're looking at distances larger than the mass of the scalars, then you don't get the cancellation because the scalars are no longer, they have a Yukawa force now, and then all you see is the massless graviton. So that says that there should be a regime above which gravity looks normal from the point of view of Newton's law, and below which there's magic in the cosmological constant. And now it happens that the cosmological constant has to cancel to the electron volt level, 10 to the minus 2 electron volt level, and which corresponds to a micron in distance. But the tests of Newton's law go down to 45 microns. And so, it didn't have to be true, but the numerics are such that, as far as we know, there's a disjoint regions. That we've tested Newton's law in a region which is disjoint from where we had to have magic in the cosmological constant problem. And I think that these models are threading that by having the extra dimension in the right place.
Would it work if the CC is larger than the electron scale?
It doesn't, but you can't understand. The spirit of that question is probably if you're asking, is there a four-dimensional way of thinking about it? So it works. This works for the energy in the brains could be as large as you like, much bigger than the Kaluza-Klein scale. But the mechanism is higher dimensional because the curvature in the extra dimensions is canceling the tension of the brain. And so I don't think there has to be a four-dimensional picture of that because you're well above the Kaluza-Klein scale. There is something in 4 dimensions that I don't know how to do yet, but which does have to be explained. If I had a very, very light particle in the brain, much lighter than the Kaluza-Klein scale, and I integrate it out and I work at the classical level in the bulk, but at the quantum level on the brain, the magic is not that I get a small cosmological constant. It's that I get 0 cosmological constant at the classical level in the bulk. And so that has to have a 4-dimensional description because that I could have done for an arbitrarily light particle. And that I don't quite see how to make. I think I'm 80% of the way towards seeing how that works, but I don't really know what that theory is. But it has to exist, I think, because the 6-dimensional theory does it. But that would certainly help clarify, again, what's going on at low energies to have that explicit 4-dimensional theory.
Okay, so maybe while Joe is setting up, we have time for one more.
Cliff, I have just one question about your naturalness. So, according to you, what is natural? Because till now, suppose if I believe that neutrinos are Dirac in nature, and I have to accept 1 part in 10^11 Yukawa for that, which is exactly the same scale. If you convert that into energies, it is 1 part in 10^44, which is the same as your cosmological constant.
Yep.
So what worries me about is what is exactly the definition of naturalness from your point of view and from my point of view or from someone else's point of view could be completely different.
There's several notions that are commonly in play.
Exactly.
And you didn't mention it, but the axion mass is also the same ballpark.
But you know that I don't like axions, I don't like singlets, but anyway.
It doesn't matter what we like, it's
Okay.
what nature tells us, right? So,
Well, nature, we have not seen axions, but anyway, let's talk about neutrinos. We have seen neutrinos.
So I think the issue is one notion of naturalness is all numbers should be order 1 in your Lagrangian, and then if you have to put in a smaller number than that, then that's not natural.
You already see this time on.
No, let me finish. So that's I think would say is an aesthetic version of naturalness, which I think maybe nature doesn't work that way. I'm talking about technical naturalness, which I think you can take to the bank. It says that if you have a small parameter, whatever it is in your theory, then the explanation for why it's small will come in 2 steps. It'll come when somebody gives you the theory of the world at very high energies, Ed Witten or somebody, he'll tell you why it's small, but then it has to stay small as you integrate out all the physics between there and where you measure that thing. And that's informative about low energies because it says that even if you've solved it at higher energies, you have to keep it small at low energies. And so if you have an unnatural thing at low energies, it means that you're getting something wrong at low energies where you have some hope of testing it. So technical naturalness, the cosmological constant is technically unnatural because the electron is the problem. It's not really at the Planck scale that the problem is. And an electron probably you thought was the best understood particle we have. But any solution to that problem is going to have to modify the electron, and so that's why there's so many experimental consequences, that anything that deals with the technical naturalness problem will be a low-energy thing which will have lots of ways to be tested. And that's specifically the naturalism I
You would
mean.
accept very small Yukawas, but you would not accept.
From my point of view, the neutrino Yukawa couplings would be perfectly natural because they're technically natural. They might be kind of aesthetically repulsive, but who am I to judge?
Okay, on that note, let's please thank Cliff again.